and Eberhard Bodenschaft at ENS and MPIDS. And like a part of the work which I present on scalar mixing was done in collaboration with K.R. Srinivasan, P.K. Young, and Matthew Clay. And the computers that were used for the simulations performed in the work were like basically these at these centers. So I'll be talking about extreme velocity and scalar gradients in fully developed turbulence using extreme scale computing. As I guess everyone knows that turbulent flows are known to spontaneously generate very large gradients, which is typically termed as intermittency or small scale intermittency, internal intermittency. And two very common descriptors of these gradients are the strain rate tensor and vorticity, which basically can be defined from the symmetric and the skew symmetric part of the velocity gradient tensor. The strain rate, for example, characterizes the local stretching and distortion, which is relevant in like mixing and dispersion problems, whereas the vorticity characterizes the local rotational motion, which is, for example, mixing in clustering of particles in cloud physics. So here I'm showing some structure of like intense strain and vorticity using DNS data. So basically, to like talk about it briefly, like from left to right, like I'm focusing on the most intense events and like successively zooming in and increasing the contour threshold, like given by the C. So at the highest threshold, like it's pretty evident that these intense gradients, they are organized in these tubes of vorticity shown in cyan. And this is like nothing new. People have known this for a long time. Also known quite for a long time is that these extreme gradients, they lead to substantial deviations from Kolmogorov's 1941 theory, which is basically like a mean field description. And since then, there have been like a spawn of many large deviation theories to describe these extreme events. And understanding them is basically like at the heart of turbulence theory and modeling, as I noted in many of these review articles. And in another context, like from the existence of extreme events is also important from a very fundamental mathematical point of view, because it has not been established yet whether the fluid equations are mathematically well posed or not. Which is to say, if Navier-Stokes equation, they like admit like smooth and regular solutions at all times, or whether can like there be finite time singularities. And as many of you probably know, that this is like one of the famous Clay Millennium Prize problems. So in this talk, basically, like I will structure it in like to answer like some of very simple questions which we sought out to like understand. So the first question essentially we want to answer is like, how extreme are basically these extreme gradients, which is to also answer like how basically small are the small scales of turbulence. And then I'll try to make some quantitative connection with the flow structures that we saw earlier, like in vortex tubes. And then I'll make some brief like discussions about like whether blowups are possible or ruled out. And then I try to extend the work to mixing of passive scalars in turbulence. So as I was talking about like extreme gradients, so from dissipation anomaly, which is defined as like which basically says that the mean dissipation becomes constant when viscosity goes to zero. It follows from a simple argument that if I take the dissipation to be viscosity times some gradient square, that the variance of the gradients is dissipation by viscosity, and if this quantity is the Kolmogorov times inverse of Kolmogorov time square. So essentially the variance of the gradients from dissipation anomaly, it follows that they scale with the Kolmogorov time scale. So then I take the quantities, the entropy, which is defined as the square of vorticity, and the sigma, which is nothing but like the dissipation divided by viscosity, and normalize them with the Kolmogorov time scale, and like plot their PDFs as a function of the Taylor scale Reynolds number, which essentially defines like the intensity of turbulence, and that is shown here. So first, I would like maybe point at the inset and see that show you guys that like when I'm looking at like really small values, the PDF approximately collapse when like we are using this Kolmogorov time scale. But when we look at like the tails of these PDFs, we can see that they extend up to like extremely large values, and both the extent and the probability of these events drastically increases as the Reynolds number is increased. Furthermore, it can be seen that like the entropy, or like basically I'll call it just vorticity, extends to much larger values than strain, the magnitude of strain, which basically is to say that vorticity is more intermittent than strain. So since we normalized with the Kolmogorov scale and we are like seeing events which are like some 1,000 times the mean, this basically kind of hints at that there are scales which are smaller than Kolmogorov scales, and that is what like we want to look at also. Just before I go deeper into that, I would also like to show that the energy spectrum also kind of reaffirms the existence of sub Kolmogorov scales, and like the fact that they cannot be described by the Kolmogorov's theory, 1941 theory. So if we look at the compensated energy spectrum, which I think like most people would be familiar with because it's like the most famous thing about turbulence very often, we see that like the wave at very large wave numbers, like there is no collapse when rescaled with Kolmogorov variables, and the spectrum essentially is like increasing with the Reynolds number. This can be seen like better here with the negative of the log derivative. So this is like some intermediate region around the Kolmogorov the scale where there is some collapse, which usually people see when they look at the collapse spectrum. But if you go to the far dissipation range, then you can see that there is actually no collapse. So before diving deeper into the results, I would like to quickly talk about DNS. So direct numerical simulations essentially is the methodology where we numerically solve the governing equations and resolve basically all the scales completely. It's nice in the sense that it gives us the full knowledge of the flow field, but of course it's also very expensive because resolving the flow field requires very like high resolution grids. So the setup that I will be using is the simple one, which is good for studying the small scales, and that of forced stationary isotropic turbulence in a periodic domain, for which we can use Fourier pseudospectral methods, which are essentially like the most accurate methods that you can use for this kind of setup reasonably. And since we are looking at resolving extreme gradients, we have to be mindful of the small scale resolutions, both in space and time. And if we want to resolve like the strongest gradient properly, then that basically comes at the cost of like decreasing the Reynolds number for the same grid size. So earlier this was obviously very difficult, and like most of the studies, like the same setup, they basically used either like very low Reynolds number or like a high Reynolds number, but like kind of under resolved. So in this study, I will mostly use data for the spatial resolution given by Kmax eta 6 to compare this with like previous DNS runs. Like usually the resolution is like around 1 or 2 to achieve like high Reynolds number. So the table basically shows the database. Like in terms of the Taylor scale Reynolds number, we have roughly like about one order of magnitude going from 140 to 1300. And this is accomplished using like grid sizes which go from 1024 cube to 12,000 cube. Though more recently, this run at 1300 has been extended to 18,000 cube with the slightly higher Kmax eta, but I will not be using that for today. So the first question, like the first simple question that like we can answer is like, how do the extreme gradients scale? And we saw in the earlier plot that the RMS of the gradient scales with like 1 over Kolmogorov. So let us like take that the extreme gradients, they scale as 1 over tau extreme, where this tau x is a time scale defined as some Kolmogorov times Reynolds to the power minus beta. So I mean, right away for beta greater than 0, you can see that this is like a smaller time scale. And then our aim is to rescale the tails of the PDF with this time scale. And that is shown here in this plot for strain and vorticity. Both we can see that they can be rescaled with this tau x for this range of Reynolds number, that the beta corresponds to 0.775 plus minus some small error bar. Okay, so without going into too much details, I just want to say that this collapse can be verified very robustly. Basically, the trick is to know that the tails of the PDFs of strain and vorticity, they can be very well fitted by a stretched exponential function of the form as like here, a exponential of minus bx to the power c, where x essentially is like, for example, omega times the vorticity times Kolmogorov time scale or something like that. And if we want to like rescale the tails by tau x, which is with this factor of r lambda, additional factor of r lambda, then one can show after like some simplified math that will happen if one can get this b to the power 1 over c from these fitting parameters for the exponential, stretch exponential, that will go as essentially r lambda to the power minus 2 beta. Now fitting this function is a bit tricky because it requires a fully nonlinear regression analysis, which can be sensitive to initial conditions and essentially converge to like some local minima instead of the global minima. So we first started off doing that, and we found that the C value essentially is somewhere in the range of 0.23 to 0.25, but with like some significant error bars. So then what we did was to essentially fix the C value, and then for like a given C value, chosen C value, this regression becomes linear, and it's like, it's very simple. And then what we do is essentially look at all the B and the C pairs, and then for that plot this quantity B to the power 1 over C, and to our surprise, we found that remarkably they all kind of collapse to the same power law, which kind of reaffirms the robustness of the fitting and of the obtained result. So basically that gives us
a small clear. So what is fx? Is it in the spectrum normalized, or what is fx and what is x?
fx is, so f of x is just like a function, and x is essentially the vorticity or the strain. So we are trying to fit f of x, this function, on over the tails of the PDF.
Okay, go on.
Does that answer?
Go on. Yes, yes.
Okay. So I mean, essentially, sorry, let me quickly show this. So this is the PDF of vorticity and strain normalized by Kolmogorov timescale, and f of x is the function, the stretch exponential function that we are fitting on over these tails, like which are like far from like the part where like you have like collapse with the Kolmogorov time, and then that function is fitted, and like we basically rescale it by, so I don't have all the details here, but it can be like found in this paper. The main result that I want like people to take away from this is that like that the tau x was derived like with in a somewhat robust manner. So the next, the question is essentially like, what is this tau x? And like, So the tau x is essentially the smallest time scale of the extreme events in the flow. And then the next question which follows is, what is the length scale? So we can derive that by realizing that, like, essentially the extreme gradients arise from large velocity difference over the smallest scale, which we can write as something like this. So the extreme gradients, they scale as 1 over tau x, and the velocity gradient, we can write as some velocity increment, some maximum of the velocity increment over like some smallest scale. And this smallest scale, eta x, is going to be smaller than Kolmogorov length scale, which is again defined here. But now the exponent is a different. So we'll call this alpha. Not to confuse you guys with like too many like new Greek letters. So inspecting the PDF of the velocity increment, like that is shown here, we divided by the URMS, and essentially what this shows us is that the maximum increments over, like, even at scales which are smaller than Kolmogorov is of the order of URMS. So we can confidently set the Umax will be the order of the URMS. And in a way, this is also consistent with the following idea that, like, the velocity PDFs in turbulence are Gaussian. So if we want to like calculate the maximum increment arising from like a Gaussian distribution, then essentially it will be of the order of like the RMS of the distribution. So substituting the Umax to be URMS and tau x to be tau k times r lambda to the power minus beta, and tau x eta x to be this, we essentially get that this exponent alpha for the length scale is nothing but beta for the time scale minus a factor of half. This factor of half essentially comes from this ratio of like URMS divided by the Kolmogorov velocity, which goes as r lambda to the power half. So this kind of gives us this alpha as basically like the value of 0.275, and this can be verified in a very very neat manner. So if we consider the PDF of this quantity, velocity increment divided by r multiplied by tau x. So the delta u by r represents some kind of a gradient, and the tau x essentially is of course the time scale for the strongest gradients. So if I'm looking at distances r which are smaller than eta x or equal to eta x, the smallest length scale or of the corresponding to the extreme gradients, then essentially this quantity will converge to the same distribution, same curve as we saw earlier from the collapse of the PDFs. And if I look at r, which is, then the deviations from the collapsed version, one can show that they will be proportional to r over eta x. I mean, which is kind of to be expected if you essentially like do like a Taylor series expansion around that. So the trick that we can like utilize is that we can try to match r over eta x for r greater than eta x for two different Reynolds number, and then see if, like, for eta corresponding to this alpha equal to beta minus half, do we get a collapse or not. So for the range of Reynolds number that I utilized here, like the ratio of the eta over eta x for r lambda 650 is essentially 1.5, approximately 1.5 times the eta over eta x of r lambda 140. So what this says is that if I take a r over eta, not eta x anymore, of 2 for 650, then that behavior should match the r over eta of 1.5 times 2, which is 3, at 140. And that is what is shown here in this plot. So these are the curves which correspond to like r over eta equal to 2 and 3. for like the Reynolds number of R lambda of 640 and 140, and we can see like there's a factor of these curves collapse for a factor of like this 1.5, which is to be expected. So that's very good, because then that confirms that this alpha that we derived in this manner matches with at least the data, what the data shows. So briefly, to compare with some of the other results in literature, there are like only like a couple as far as we could find. So one comes from the multifactorial formalism, which essentially assumes the velocity increment is Holder continuous with some local Holder exponent h, and then the smallest scales can be obtained by corresponding to the roughest Holder exponent, which is like the h min, and that basically gives a relation of beta equal to 2 alpha, which is a bit different than what we had. We had like alpha equal to beta minus half, and like many some papers have earlier conjectured that the h min essentially would be 0 for turbulence, and that gives beta equal to 2 alpha equal to 1. Like, I have not shown the derivation, but like one can look it up if if they want to. What this gives is basically that beta is 1 and alpha is 0.5. And what we got was beta equal to recall 0.77 and alpha equal to 0.27. So like both beta and alpha that we obtain are like a bit weaker than this quantity here. I mean, this value here. And there's also this theory from Yakhot and Srinivasan 2005, which also gives like an alpha of 0.5, which is similar to this. So as I said, the current data shows like a weaker scaling than above. And in fact, this weaker scaling with respect to these predictions is also consistent with some earlier studies at comparatively like low Reynolds number by like Schumacher and Donaldson and others. So I have not discussed that in detail, but like the main takeaway is that these scalings, which these theories like derive, they basically assume like a local cutoff Reynolds number of 1, given by this quantity like some increment times the distance over like viscosity equal to 1. And this does not really appear to be valid when we look at these intense gradients in like that we have done, for example, in vortex tubes, which is also consistent with the result of Jimenez from like 1993. And there's another thing to consider, that this multifactorial scaling, basically like Holder continuous, could be applied in the inertial range, but it's not really applicable in the viscous range, where essentially it will be continuously differentiable instead of being alpha, instead of being like Holder continuous. So then we said like, if we can try to explain the results we have like in a slightly different manner, and instead of like relying on like some abstract description, like why don't we try to relate it to like the flow structures that we already saw in the flow. So one idea is to essentially interpret this eta x, the smallest length scale over which the gradients are occurring, as the radius of some vortex tube, the smallest possible tube. And then if we invoke like the simple idea from Burgers, then this eta x is essentially going to result from the balance between the viscosity and the strain. In fact, I say Burgers, but this is actually also what the Kolmogorov scale does. Like if I replace S by some dissipation, like, and then this relation will essentially reduce to, if I replace S by mean dissipation, then this relation essentially will reduce to nu cube over dissipation to the power 1/4, which is nothing but the Kolmogorov scale. So basically, in a way, what we are saying is, let's define this eta x by not using the mean dissipation, but instead using some other dissipation. So yeah, as I said, like the mean strain essentially reduces eta x to Kolmogorov. So one can also, so the other extreme would be to assume that the S max is as the strain acting on the vorticity is essentially as strong as this 1 over tau x, which is essentially the time scale of the, or essentially the strength of the gradient, the maximum possible strength of the gradient. And if I substitute that back in this expression, after some simplification, we kind of arrive at the multifactorial result, which is like beta equal to 2, alpha equal to 1. So the results that we have basically show that we are somewhere in between these two extremes. So in a way that implies that the strain that we want to, that the average strain acting on these vortex tubes is also basically somewhere in between. So then we sort out to like look at like how like strain and vorticity interact with each other. And on the left, what I'm showing is the vorticity condition on strain, and basically it's this is at for a very large dynamic range. But let's just focus on like the large values. And what happens at large values is that this guy essentially goes as like a very simple power law, which is to say that like the strain, if strain is large, then the corresponding vorticity is also equally large. And then if we do the inverse condition strain on vorticity, then we see that it actually is not as large. It goes as like some power law, roughly in the range of like this large values, where the exponent is less than 1. So what this tells is that the strain acting on vorticity is in fact weaker, which we kind of were expecting based on the earlier result. And so this exponent gamma is actually also changing slightly, very slightly with Reynolds number. For the insight, I mean, it's shown in the insight, and it kind of goes from 0.6 to 0.72 over this range of Reynolds number, which I'll show why it's important a bit later. So writing the same expression again, that the eta x that we have can be written as some viscosity divided by strain to the power half. So instead of using S to be the mean value or the most possible extreme value, we will instead use this conditional value where we'll say that S square conditioned on omega goes as omega to the power gamma. Sorry. And this omega essentially is the one which goes as the extreme gradient that we saw earlier. And if we substitute these guys in this expression, what we end up is with this beta equal to 1 by 2 minus gamma. And if we use the gamma values which I showed earlier here, then approximately the beta that you get is very close to the beta that we have from the earlier collapse of the PDFs. So basically, it's a very self-consistent behavior across the R lambda that we have. But this kind of raises an interesting question of like what is happening with this gamma as a function of Reynolds number. So the R lambda here is 140 to 650, and like if you look at this paper in PRF, then we also have 1300, and that one barely changes from this 0.72 to 0.75. So if we try to extrapolate what will happen at like basically infinite Reynolds number, then we kind of come to the conclusion that this gamma might approach 1, but very, very slowly. Basically, like at extremely large Reynolds number. Like based on some fitting, we got like something like 30,000 or something like that. Which is impossible to verify because 30,000 doesn't even exist on Earth. But the interesting result from this is that in the limit of R lambda tending to infinity, like we kind of come back to this result that was obtained from some of these theories. So in a way, to basically tie this up, what it's saying is that these theories are valid only in the extremely large Reynolds number limit, which are kind of, I would not say impossible, but almost like close to impossible to verify from like real data. Uh, so to talk about like the possible blow-ups in the same line of work. So one of the mechanism which leads to these strong very gradients is the vortex stretching mechanism, and that can be shown like basically writing this vorticity transport equation where we have this omega dot s, and if we write the equation for vorticity squared, then we have this omega I omega j sij. So this is essentially the nonlinear interaction of vorticity and strain, which leads to extreme gradients. And one of the questions which I had posed earlier was like, can these gradients blow up? And if they blow up, essentially it has to come from this nonlinearity. And if we simply assume that strain is same as vorticity, as we know it's not true, but just for the sake of argument, let's do that, because they are like both gradients, and like we take like inviscid flow, then we get like a very simple toy equation like d omega dt equal to omega square, which has the solution omega goes as 1 over t star minus t. So if t star is t, then essentially the solutions will blow up in finite time. But we, as I said earlier, I mean just before, like we saw that the strain does not go as vorticity, and in fact it's weaker than vorticity. So we set out to like explore that why is that happening. So note that like vorticity and strain, like this equation is local. Like this equation applies at like every spatial point in the flow, but the relation between vorticity and strain is actually non-local. And by non-local, what I mean is that we can essentially write the strain rate as a Biot-Savart integral over the vorticity field. So this integral essentially is a global integral over the entire domain. So at even though at every point we are writing this omega j sij, the relation between the two is actually connected through the entire flow. I mean, which is to be expected because we are looking at incompressible flows. So some people would express the non-locality through the pressure field, but as I'll show, like this one also works. In fact, it works like in a better way. So in order to essentially compare like what or essentially in order to isolate the local and the non-local effects, what we do is we consider this simple decomposition. So if I take a point of origin, then this integral essentially goes from 0 to infinity. And what we want to do is break up this integral into 0 to some capital R and then R to infinity. So essentially giving us some kind of a non-local contribution, which can be interpreted as like some kind of a background strain acting on these vortex tubes. And then there's this local contribution, which is essentially like the strain induced by vortex stretching in its neighborhood, in the neighborhood of these vortex tubes. And then again, the amplification term can be split in this way. So if if vorticity squared were to amplify to very large values, then this guy has to be, of course, like very strongly positive. And this guy basically is a sum of these two terms. So basically what mathematicians do is try to establish like bounds on like these nonlinear terms. And if we can establish bounds, then basically that means that you cannot have a blow up because it's bounded. So actually this work by Constantine and others in 1996 has already established a bound on this non-local contribution in terms of the total kinetic energy of the flow. What remains to be done actually in solving the regularity problem is like figuring out what this local contribution does. Uh, so that is what we like seeked out to do, essentially like get this local contribution term as a function of r and also the magnitude of the vorticity. So in principle, this quantity like shown here has to be evaluated by this complicated global integral for like many different values of r, which can be like also inaccurate and like also like very time consuming in terms of like resources. But recently we were able to show that these integrals can be evaluated without performing the integral, the Biot-Savart integral in a very like neat and efficient manner. So I'll skip the details of like how it's evaluated, but I'll just like show some quick results. So in the top row, what we are showing is the entropy, and the first frame shows like the familiar two cube-like structures for some nominal entropy of like, this is like a moderate event like of 200, and then like this 1000 essentially is like a more extreme event, and we can see that they basically have, the tubes have shrunk to a smaller size. And this is like a cross section at the midplane, which kind of shows the variation of the entropy across the tube. And in the bottom row, for corresponding to these events, what I've plotted is the local contribution, the nonlinear amplification term from the local strain. And we can see that for like a moderate value of entropy, there is like a plus minus field. But when we look at like a stronger entropy, what happens is that the negative field starts dominating compared to the positive field. I'm sorry. And that can be seen very nicely in this cross section, where if we look at like the core of the vortex, where the entropy is the largest, like at the center, then we can see that at the center, this non-local amplification, sorry, the local amplification term is extremely is dominantly negative. So I mean, essentially the same result is now being plotted here for like a bunch of different Reynolds number and like some R values. And what the main takeaway is essentially that this local amplification term is predominantly negative. And if you recall that this term, it arises from like the, in a way it's self-induced because of the vorticity near the tubes. So what this tells us is that essentially when the vorticity becomes very large, it kind of like self-attenuates itself to prevent a blow up in the neighborhood of these tubes. So this is actually very interesting, because what this tells us is that if this can be mathematically formalized by understanding like the physical origin, then that would essentially establish the regularity of Navier-Stokes equations. To briefly summarize the first part of my talk, so what we saw is that the extreme gradients in turbulence scale as r lambda to the power beta divided by the Kolmogorov time scale, where beta is some 0.775 over the Reynolds number range of 140 to 650. And we also saw that these gradients are arranged in vortex tubes, where the velocity jump across the tubes is like of the order of the RMS of the velocity. And this distance, and the distance over which this happens is the Kolmogorov length scale divided by r lambda to the power alpha, where alpha is this beta mass alpha. So though I have not written it down here, in a way, what this also tells us that it's not enough to resolve the Kolmogorov scale when we are doing simulations, if we want to look at the extreme gradients. we need to actually resolve better than Kolmogorov scales when we are like running these DNS simulations. And to explain this origin of these exponents, we basically looked at like the interaction of strain and vorticity in the flow, where we found that the strain acting on vorticity is comparatively weaker with some exponent gamma less than 1, and we could relate this exponent with these alpha and beta that we found earlier. And finally, we explored the non-local interaction between strain and vorticity by invoking the Biot-Savart relation. And the surprising result here was that, like, when looking at the local component of the vortex stretching, we found that it actually opposes the amplification of vorticity instead of like aiding it, which essentially could be an important ingredient to establish the regularity of equations. So so that is with the velocity field. And what I would also like to briefly do is extend some of these ideas. Not possibly, I guess I won't be able to discuss everything, but like I have like some few slides to basically look at the mixing of passive scalars or scalar turbulence. So passive scalar essentially is like a scalar, like for example temperature, or like some concentration of, like for example, salt in water, which we are assuming is passive, which is to say that it does not influence the velocity field. And in that case, the Navier-Stokes equation stays the same, and the equation by which we can evolve the passive scalar is given by this equation here, where there's this forcing term because of the mean gradient, and then of course there's a diffusive term where d is the diffusivity of the scalar. And apart from the Reynolds number, the dynamics of mixing are now additionally governed by a new non-dimensional parameter called the Schmidt number, which is just the ratio of the viscosity and the diffusivity. And this quantity actually varies across like a very, very huge range in nature and in engineering. So for like liquid metals and like convection in the sun, the Schmidt number is like extremely small, than compared less than 1. And for like day to day, what we experience like in gas phase mixing, it's like order of 1. And in liquids, for example, like dyes, or like if we consider like salt in the ocean, then this Schmidt number is much, much larger than 1. So of these three regimes, what I'll focus on is the regime of like Schmidt number much, much greater than 1, which is actually computationally very challenging, because as the Schmidt number becomes greater than 1, the scales in the small scales of the scalar field, they actually become increasingly smaller compared to the smaller scales in the velocity field. So based on the Kolmogorov phenomenology, sorry. Okay. So based on the Kolmogorov phenomenology, the smallest scale in the scalar field is often given to be the Bachelor length scale, which is essentially the Kolmogorov length scale multiplied by this Schmidt number to the power minus half. So as you can see, if I'm looking at, for example, a Schmidt number of 100, this is a factor of 10. So the Bachelor scale already is 10 times smaller than the Kolmogorov length scale, just at a Schmidt number of 100. And like, for example, in the mixing of salt in ocean, the Schmidt number is like of the order of 700. So like to capture that at a modestly high Reynolds number, it's extremely difficult in numerical simulations. So actually, before I talk about numerical simulations, let me give a brief setup of the problem. So based on the Kolmogorov theory, we often assume that the small scales are locally isotropic. So in case of the scalar mixing, what that implies is that the small scales should not be affected by like an imposed mean gradient at the large scales. And for the scalar gradients, what does actually, sorry, I didn't say the scalar gradients, but what this implies is that the even moments of the scalar gradients are equal in all direction, whereas the odd moments will be zero. I mean, this essentially comes from like the isotropy of the scalar gradient tensor. However, what experiments and simulations have shown over the years is that the skewness, which is the third moment of the scalar gradient in the direction of the mean gradient, is actually not zero, and it's finite for Schmidt number one. And this happens because of, this can be connected to like the presence of these Ramcliffe structures in the scalar field, which don't go away when the Reynolds number is increased, which is to say that the skewness doesn't change even if you go to extremely large Reynolds number. So the Ramcliffe structures kind of look like what I've shown here. Like essentially, if you go along the mean gradient, then you find that the scalar fluctuations shown here, they jump up suddenly at a very small distance, over a small distance, and then they relax before like jumping up again, and this kind of repeats itself. So another observation is that the skewness decreases with Schmidt number at a low Reynolds number from what people have seen, and that is what we are like kind of interested in this work, and I'll show like more of it later. So as I had mentioned, like the DNS of these high Schmidt number scalars is like extremely expensive because you have to resolve like much finer scales than even Kolmogorov. So what we do is like a setup of this kind where we say that, okay, let's take a coarse grid and resolve like the less than equal to Kolmogorov for the velocity field. And for this, we'll use like a conventional Fourier pseudospectral method. But instead of solving for the Schmidt number on this grid, we will solve for the high Schmidt numbers on a finer grid, for which we will not use the pseudospectral methods because they are very expensive. But instead, what we will use is a very high order compact finite difference scheme. So essentially, by decoupling the velocity and the scalar field on like grids of different resolutions, we have kind of like elevated the problem to like some degree, because now we are not solving the velocity field on like the very fine grid, which conventionally is what people do. So this reduces the cost of the DNS like by like a huge margin. And what we have done is also accumulated a database, which for this case goes up to grid sizes of 8192 cube grids. And basically the Reynolds number for like the range of the Reynolds number is 140 to 650, the same as what we saw before. And for each Reynolds number, we try to go up to as high Schmidt number as possible, while ensuring that we are resolving the smallest scales completely like accurately. So the largest range of R Schmidt number that we could accomplish was for R lambda of 140, where the Schmidt number goes from 1/8 to 512. And this is what I will mostly use to like discuss the results. So talking about the Ramcliffe structures, so on the left, essentially, these are the Ramcliffe structures from DNS for Schmidt number one. And from top to bottom, the Reynolds number is increased from 140 to 650. And we can see that like at all Reynolds number, the cliff and the ramp structure is like very clearly visible. And like at higher Reynolds number, there is like more small scale motion, but the ramp cliff structures clearly like still persist. In contrast, if I fix the Reynolds number and increase the Schmidt number, like in this right frame, it goes from 1 to 512. What we see is that the Ramcliffe structures are increasingly overwhelmed by the small scale motion. Like in the background, there is some semblance of like a Ramcliffe structure, like for example, like at the highest Schmidt number of 512, but it's completely dominated by the small scale motion. So based on this observation, we asked ourselves like if we can like come up with like a simple model to explain the scaling of the scalar gradient moments. So the model essentially looks like this, where we have taken like a ram cliff. The cliff is here, and we are saying that the cliff happens over some distance delta, and the jump of the scalar across the cliff is some delta theta, and the size of the ram cliff combined is of the large scale of the flow L. So the volume of the cliff occupied here is delta over L. So if I were to like take the some pth order moment which is odd across this ram cliff, then what would happen is that this volume, this gradient at the cliff, which I'm calling like this nabla theta cliff, which is delta theta by delta. So that will be the only one which will be remaining, and essentially assuming that the small scale motions are kind of, if I look at like odd order moments, they cancel off each other. So using that simple idea, what we can say is that the odd moment parallel to the mean grade, like where we have this ram cliff to the power p, is given by this gradient at the cliff only multiplied by this delta over L, which is the volume of the cliff. And once again, like we basically can take this the jump delta theta to be the RMS of the scalars, because similar to the velocity, the distribution of the scalar also is also a Gaussian. So that reduces to the odd order moment essentially reduces to this theta RMS by delta to the power p times delta over L. And if we normalize it in this manner by theta RMS over the Bachelor length scale to the power p, then after some simplification, what we get is this expression that eta b by delta to the power p minus 1, which I'll come to. But otherwise, we get this Schmidt number to the power minus half and r lambda to the power minus 3 half. So for the data that we have, we can like at least satisfactorily explore the Schmidt number dependence. So the first assumption essentially is to, sorry, I didn't write it here, but if we just take delta to be eta b, saying that this jump happens over the assumed smallest scale in the scalar field, the Bachelor length scale, this term goes away, and this normalized moments, they basically go as Schmidt number to the power minus half. So that is what is shown here for the R lambda 140, and the Schmidt number essentially is like from over 3 orders of magnitude, and this dashed line is the slope of minus half. And these 3 set of curves are like 3rd order moment, 5th order moment, and the 7th order moment. And then we can see that reasonably, we can say that the 3rd order moment is maybe like close to this minus half scaling, but like by the time we are at the 7th moment, then the scaling is like is substantially different from this minus half. So clearly the assumption that the size of the cliff delta equal to eta b didn't work out, and what this is telling us that the delta has to be greater than eta b. So one way to justify picking a different delta than eta b is to recall that eta b is defined by saying that the time scale of diffusion, eta b squared by d, is the same as the Kolmogorov time. But the Kolmogorov time, of course, is defined from the mean dissipation. And as we saw, that doesn't characterize the time scale of the strongest gradients, which is different than, like, smaller than Kolmogorov. And in a way, this adds up because it has been shown many times that these cliffs are formed when from the velocity field corresponds to like strong dissipative motions. So instead, what we will do is we'll define some correction over the Bachelor, and we'll define this eta d for diffusive multiplied by some Schmidt number to the power alpha. And in terms of the Kolmogorov, it's basically minus half plus alpha. And in the earlier expression, if instead of now if we use delta equal to this eta d instead of eta b, we end up with this expression where we have like Schmidt number to the power zeta p, where the zeta p has the minus half scaling that we saw earlier, and on top of that it has like some additional factor which depends on the moment of the order, and also the order of the moment, and also this alpha. So the question basically is now, what is this alpha? So in order to calculate what alpha is, or to evaluate alpha, we recall a very well-known result about the scalar dissipation anomaly, which basically says that if the diffusivity is made small, then the scalar dissipation rate should like still like be finite, similar to like the energy dissipation anomaly. But based on like some semi-empirical arguments, it is essentially shown that that is not precisely the case. And in fact, the normalized scalar dissipation, when normalized by the large scale quantities, it goes something like this, like r lambda to the power, there's like this log Schmidt number correction. Now note, this expression was kind of defined by making a lot of like empirical assumptions about like how like the spectra behave and things like that. But the bottom line is, if we try to derive the second moment, which is the same as the dissipation divided by the diffusivity, and normalize it by this theta RMS by eta b square, mathematically we can say that this guy depends on the Schmidt number with some negative exponent, which is essentially replacing this log dependence by like a power law dependence for like the sake of convenience. And then we argue that this eta d, which we defined earlier, can be defined in a way such that it actually upholds the scalar dissipation anomaly by absorbing this additional dependence that we see here. And if we do that, then what we end up getting is this alpha that we defined as the correction. It can be obtained in terms of this dependence of the second order moment by this factor of 2. So the second moment normalized by this quantity is shown here, and we can see that it actually follows a power law like extremely well with the exponent of minus 0.1, which gives this alpha correction to be 0.05. And if we go back to the earlier result, and if we plug in alpha equal to 0.5 in this expression that we had derived, then remarkably, we essentially get these exact power laws that were fitting these moments. So, I mean, it leads to like a really, really good agreement from with the theory. And just to show like it's not just like the odd order moments, in fact, we can also collapse the tails of the PDFs with this new scaling. So here I'm showing like the gradient of the scalar parallel to the mean gradient and perpendicular to the mean gradient. And in both the cases, we have normalized it by this theta RMS by eta d. And if I look at the parallel, what we see is that on the plus side, they all collapse very well. And on the negative side, there is like obviously like a Schmidt number dependence. So this is happening on the negative side because of the departure from local isotropy at low Schmidt number, but that high Schmidt number, the odd order moments kind of like saturate to like a symmetric behavior with respect to the positive side. But the the gradients in the perpendicular direction, for that we see that both the sides of the PDF collapse perfectly with this rescaling, because for the direction perpendicular to the mean gradient, there was no the odd order moments are already 0, so the PDF is automatically symmetric. So based on the collapse of the PDFs, we can also essentially look at the higher order moments in both the directions, even moments, and we can see that they also like collapse and are like constant with this scaling. So basically, to summarize, what we are showing is that we can develop this model based on the structure of the scalar field, which allows us to quantify the scaling of the scalar gradients as a function of Schmidt number and R lambda. And this model surprisingly captures all the statistics extremely well over like 3 decades of Schmidt number that we have investigated. And the major outcome of this is that the smallest scale in the scalar field is arguably not the Bachelor scale, but like a very small correction to it with this exponent of 0.05. So it might look like a very small correction, but I would like to point out that when we look at the velocity field, the correction compared to, for example, the Kolmogov's theory for second order moments or like things like that, they are also extremely small. But it's only when we go to very high order moments that these small deviations, they add up to become like a substantial deviation. So this is to be interpreted in the same spirit. So this of course, this relation kind of requires like a more deeper theoretical development to accompany, which is ongoing. And of course, we also would like to have some data at higher Reynolds number to make sure like that this guy is consistent across like even higher Reynolds number. But yeah, I think I will just conclude my talk with that, and like I guess I'll like have take any questions.
Okay, thanks, Dhawal. So let's quickly go to question answer. The recording is still on, but I will stop after question answer.
Sure.
So please go on.